does it mean to be a root of a polynomial? Landon wants to close your Chromebook, Anna, we close your Chromebook. What does it mean to be a root of a polynomial? So I touched on this, I think, last week. And I said we're going to get to this a little bit more, but I specifically used the term root. Ava. It's what? The x, what about the x? Okay. Zeros, okay? So roots, simply all that means are zeros of the function, which we've been doing over and over and over. Okay, so roots, zeros means the exact same thing. It's where it's crossing the x-axis, if you thought about it graphically. It's where my y value will equal 0, or where my function will equal 0 as an output. Okay, so roots, when you see this rational root theorem, it's talking about zeros. What does rational mean? What's that? Yes. So if I said something was rational, if I said I had a rational function even, okay, not thinking like rational numbers, irrational numbers. Rational simply means a fraction. Okay, so we can have some fractions now going on. So rational simply means fraction. So like 1/4, that's rational. Okay, so we're going to be working now with rational, which means we're going to have possible fraction answers. Okay, so like even 2 I could write as a rational and just write it as 2/1. So even if it's an integer, a number, I could write it as 2/1 and it's a fraction. Okay, so rational root theorem, we're going to get some fractions we're working with. Root meaning zeros. Okay, so let's talk about the rational root theorem. So first off, we're just going to work with some polynomial equation, p of x, which we've been doing all along. So I could say p of x is x cubed plus 2x squared plus 7x minus 3, whatever. Okay, at p of x, this means we're working with some sort of polynomial with integer coefficients. Coefficients, remember, the numbers in front of our variables. Oh, this should be 7x. And integers are not fractions. Integers hit right on the number. 1, 2, 3, 4. So we are going to work with a polynomial with integer coefficients. Okay, we know there are a limited number of possible roots. So if this is a degree 3 polynomial, how many possible roots could there be? 3. Okay. Zeros again whenever our function is equal to 0. Okay, what x values can I put in and I get an output of 0? Okay, if we thought of it graphically, y is 0, it's not above the x-axis, it's not below, it's sitting right on it. Okay, and again, where it's crossing that x-axis. Okay, so the rational root theorem tells us integer roots must be plus and minus factors of the constants in p of x. Now, when I've written up there that function p of x, x cubed plus 2x squared plus 7x minus 3, what's my constant in that expression or that polynomial? What's the constant term in that one? Jake, what do you think? Not x. Nope. A constant, meaning it doesn't change no matter what x I put in there, it's always going to stay the same. Correct. So this right here is the constant. Okay, it doesn't matter what I put in for x, that -3 is not going to change. That's why it's called a constant. Okay, integer roots must be plus minus factors of it. What are my factors of 3? 3 and 1. Okay, but when it says plus minus factors of it, it means it's going to have plus minus 1 and plus minus 3. So that's what that statement is saying. Integer roots. Okay, so my roots that will be integers that are not fractions, not rational. Integer roots must be plus or minus factors of the constant. So these are possible ones. My rational roots, which is what we're going to focus on, will be plus or minus now factors of the constant divided by factors of the leading coefficient. In my example that I've written up here, this p of x polynomial, what is the leading coefficient? 1. Okay, so right here, that would have been the leading coefficient. So no matter how complicated or how long your polynomial is, all we're looking at is the leading coefficient and the constant on the end. I don't even care what's going on in the middle. The rational root theorem tells me that I could have integer coefficients, which are simply plus minus factors of the constant, but then rational roots will be plus minus factors of the constant divided by factors of that leading coefficient. So these problems get a little tedious. They seem like a lot, but you'll get better at it and you'll start to identify efficiencies in working through the problem. Not shortcuts, but you'll start to recognize what's happening with it and you'll progress through it quickly. Okay, all right, so finding a rational root. So now we're talking about integer roots at all. We're talking about those rational roots explicitly. List all possible rational roots of this polynomial. 2x cubed minus x squared plus 2x plus 5. Okay, you don't have to write this down a second time because you already have it in your notes. But just a reminder, the rational roots are the plus minus factors of the constant divided by factors of the leading coefficients. What are the factors of my constant? Correct. Plus or minus, I'll just write them in order. Plus or minus 1, plus or minus 5. Okay, it's constant, I can only do 5 times 1 to be able to get 5. What are the factors of the leading coefficient? What number is my leading coefficient? 2. So my plus minus 1 and plus minus 2. Do not forget the 1 as a factor. Okay? You're essentially always going to have plus minus 1 in constant factors and leading coefficient factors. You'll always have, because 1 is a factor of every number, but we want to include that. So my possible roots, possible rational roots, it's going to be this fraction, factors of the constant divided by factors of the leading coefficient. So I have to go through this one by one. Okay, so I could do 1. Now let's work it up here a minute. So if I took my positive 1 and divided it by positive 1, I end up with 1. Okay, so this was the constant plus 1, and then the leading coefficients plus 1 from the second row. Okay, and so I can do positive 1 or I could do negative 1. So I'm going to say plus or minus 1. But then I also have to do plus minus 1 for my constant divided by plus minus 2 for my leading coefficients. Okay, so I'm going to have plus or minus 1/2. Oops, plus minus. And then I go to the 5 for my constant factor. So plus minus 5 divided by plus minus 1 is just plus minus 5. And then plus minus 5 divided by plus minus 2 is plus or minus 5/2. So these are all possible roots. These are not guaranteed that every single one of these are roots, because we know there's actually only going to be 3 roots because it's a degree 3 polynomial. But it's going to be 3 from this list here of 8 possible roots that I've listed out. All right, let's do another one for practice. Determine what our possible roots are. Okay, I'm going to step in to make sure we're on track. So my constant is 2. So my only options here are plus minus 1 and plus minus 2. My leading coefficients, I'm going to have plus minus 1, and then I'll probably just do it this way to keep it in order, plus minus 15. And then I could also do plus minus 3 and plus minus 5. What's that? Both factors. Yep, list them both out. What can you multiply to get there? All right, so now my fractional piece, I need to work through every single one. So if I start with the ones, plus minus 1 divided by plus minus 1 is still plus minus 1. Plus minus 1 divided by plus minus 3 will be a plus minus 1/3, plus minus 1/5, plus minus 1 over 15. Is everybody comfortable how I got all of those? So I essentially checked off using the 1. Now I have to do plus minus 2 over 1, which is just plus minus 2, plus minus 2/3, plus minus 2/5, plus minus 2 over 15. I've listed out 8 plus minus possible roots, but that means there's actually 16 possible roots. We know there's only going to be 3, and it's going to be 3 out of this list of 16. Exciting? Are you thinking, what's the point of all of this? Okay. It's time to take this to the next.
Are we going to have to find which one?
Yep. So actually using now the rational root theorem. Okay, so this one's we're gonna do one problem over multiple slides to how we actually use this. Okay, so the question will be something as simple as this. State the possible rational zeros. So that's what we just did when we came up with that list of 8 plus minus roots, 0, same thing. And find all of the zeros. So then we had that list of 16. We have to figure out, okay, which of those 16, which 3 were actually the roots. So now we got this problem, 15x cubed minus 32x squared plus 3x plus 2. So again, first step, let's come up with all the constant term factors and the leading coefficient factors. So this would just be plus minus 1, plus minus 2, my leading coefficient, plus minus 1, plus minus 15, plus minus 3, plus minus 5. Okay, this is what we just did this problem. So possible rational roots, we're going to have plus minus 1, plus or minus 1/3, plus or minus 1/5, plus or minus 1 over 15, plus or minus 2, plus or minus 2 over 3, plus or minus 2 over 5, plus or minus 2 over 15. Okay, this is really just a duplicate slide. This is what we just did on the last slide. All right, so now I just listed this out, same problem. Now we need to test, and I say test each, but really once we find the first one, we're good. So test each possible rational root in P of x until you find a root that when you put that in for x, your polynomial ends up being 0. So this is a continuation of that remainder theorem that we talked about 2 days ago. Okay, if I put a value for x in and my polynomial ends up being 0, through synthetic division, I would have got a remainder of 0. What that means is it is a root. That x is a root. That's where it's going to cross the x-axis. All right. This is the semi-tedious process now where you just have to test them. Okay. And so I just go right down the list. So let's try P of 1, because I could have a positive 1 or I could have a negative 1. If I do P of 1, putting right back into my equation, so that's 15 times 1 cubed minus 32 times 1 squared plus 3 times 1 plus 2. I'll tell you, when you work this one out, you get negative 12. Yes?
When you get the radicals, you multiply by the x before you use the exponents, correct? Or would you
No, you do exponents first. Parentheses, exponents, multiplication, division, addition, subtraction. PEMDAS.
That's
So-
what I've been doing wrong. Okay.
Yep, you do the exponent first and then multiply.
There was an equation where you were like, you have to make sure that you multiply first and then do the exponent. It was like the, I don't know what it was. It was the,
Okay.
the equations. But-
Okay. All right, so let's try negative 1. If I put negative 1 into my function, I end up with a negative 48. Okay, I want it to be 0. So this is telling me that positive 1 is not a root and negative 1 is not a root. This big long list that we created were simply possible roots. All right, so let's try another one. Let's try it at 2. There's not a shortcut. Correct. So you are only going to do like one of these on the test because they take a while. Okay? And I only give you 2 homework problems today plus some IXL that's quick. Okay, so if we tried 2 into here, okay, so I just go down my list. If I try 2, that does work. Okay? So that one gets me an answer of 0. Okay? So that tells me, so 2 is a root. All right, that's important. That's telling me now at 2, I know it's going to cross. It's going to cross the x-axis specifically at 2. So we did all this work, and we found out 2 is a root. Once we find a root, we can move on. Okay? You don't literally have to test each. When I say test each, it's really test each until you find one that equals 0. Once you find one that equals 0, boom, we're going to move on. We don't have to keep doing this. Okay? So this is a little tedious right here, but you have to do it. Okay? All right, so we know in our function P of 2 equals 0. So we know 2 is a root. So I can also build on this and say, I know x minus 2 is a factor. So this is pulling together stuff we were doing back even in chapter 4. We would factor it out into a binomial. We would solve to figure out where my binomial equals 0. So do not mix up this step. If I get 2 as a root, my binomial is actually x minus 2. Okay? X minus 2 now is a factor. So now we can use this using synthetic division to find other factors. So I'm going to make my press box. X minus 2, the first step in synthetic division is to reverse the sign, or it's simply whatever you had in here. So P of 2. So in my press box is going to be a positive 2. So however you remember that, if you write it as a binomial and reverse the sign, or you know that number is a root, that's what goes in your press box. Synthetic division lets me say 15, negative 32, 3, and a positive 2. And it went x cubed, x squared, x, and x to the 0. So I know I don't have any zeros that I have to put in here. Bring the 15 down, that becomes 30. And remember, I'm adding. So this is negative 2. This becomes negative 4, negative 1, negative 2, gets 0, which is what I want. Okay, assuming this is kind of a checkpoint to make sure you did your synthetic division right, because you already proved that 2 is a 0 of it. So when you do your synthetic division, you should get a remainder of 0. If you don't get a remainder of 0, you messed up somewhere, you got to backtrack. So from this, I can build my polynomial. And so I have 15x squared minus 2x minus 1 times x minus 2 is equivalent to this 15x cubed, 32x squared plus 3x plus 2. Let's see if we can factor this. Is this factorable? So negative 15, let's go to this. Negative 15 that adds up to be a negative 2. Two numbers I can multiply to get negative 15. Landon. Okay, so negative 5 and 3, or 3 and negative 5. Doesn't matter which order you put it in. Okay, but because it was 15x squared, I can't immediately go to say x minus 3x, or I'm sorry, x minus 5x plus 3. So we have to continue this on. So 15x squared minus 5x plus 3x minus 2, and we're going to do our factor by grouping. And so if I factor out, I can factor out a 5x. Thank you. Getting ahead of myself. Minus 1. That'd make a difference. So this would be 3x minus 1. This becomes 3x minus 1. Conveniently, all I had to do was factor out a 1 from that, and it's a positive 1. So I end up with 5x plus 1, 3x minus 1. So this is 5x plus 1, 3x minus 1 times x minus 2. It's a long problem, isn't it? We're not done yet. Okay? Because remember, we were trying to find all the zeros. We're really close now. Okay? We're really close. Okay, so we factored this out, determine the roots in factored form, so we just did that. So this is x minus 2, and we know that this is 5x plus 1, 3x minus 1. So my zeros are going to be x equals 2, which we already knew. And then this one is going to be x equals a negative 1/5. And then this one becomes x equals a positive 1/3. And we are done. Okay, so that was one problem. I'm giving you 2 for homework today, plus some IXL stuff, but the IXL stuff is just like finding factors, stuff like that. But actually working a problem start to finish, this is what it looks like. Okay, so I'm going to ask you to list all possible rational roots, test the roots until you find a 0, do synthetic division, completely factor, find the zeros. Okay, so this one ended up being pretty long, but that's what they're going to be. All right. So my quick little roadmap. Maybe take a second to write this down. Okay. So step 1, constant term factors and leading coefficient factors. That's the first thing you want to figure out. From that, we do that fraction where we divide our constant term factors by the leading coefficient factors, and those are a big list of all possible rational roots. We have all those possible ones, and we start picking them off one by one. Simply put it right into the equation. Until you get an answer of 0, you have to keep going. But as soon as you get an answer of 0, you can stop. You're done with that step. Once you have that 0, put it in with synthetic division. Synthetic division is really allowing you to factor. So now we'll get our factors of our polynomial. We will not have a remainder, because that was the whole thing in step 3, is eliminating the remainder. And then lastly, determine the roots from that factored form. All right, so you can see how everything's coming together that we needed to, stuff we were tested on yesterday, we need to be proficient in that in order to do these types of problems. Okay, does everybody have these steps down, or you need another minute, or? Okay, I'll put these slides on School of You too. All right, so let's do one example, one more example, and then you'll be off and running. So set up to the problem. State the possible rational zeros and find the zeros. And this will be what I'll ask on a test. I'll say, give me all the possible ones from that possible list. Tell me which ones are actually the zeros. Okay, so first off, we need to find constant term factors and leading coefficient factors. So my constant term here is 4, and you don't have to worry about that it's -4 or +4, because your factors are still going to be that plus minus piece. Okay, so my constant are going to be +-1, +-4, and +-2. You don't have to write the 2 twice. We know it's 2 times 2, so 2 is a factor. My leading coefficients, in this case, my leading coefficient is only 1. Okay, so +-1 is going to be my only factor that I'm going to have for my leading coefficient. Possible rational roots are the constant divided by leading. Well, 1 is my denominator for all of these. So my possible rational roots are simply +-1, +-2, +-4. You don't have to write them 1 over 1, 2 over 1, 4 over 1. Okay, so in this case, I only have 6 possible ones. Of that 6, 3 of them are going to be the actual roots. So let's start testing them. So if I did P of 0, or let's go P of 1, sorry, not 0. P of 1, I will tell you, is -6. Simply putting it in there. If I did P of -1, I get 0. That's what I want. Okay, so I know -1, so -1 is a root. And because -1 is a root, I'll say x plus 1 is a factor. So make sure you're making that connection to, once we find the root, if we were to write it as a binomial, that's the factor piece. So we have to pay close attention to those signs. All right, factor using synthetic division. And so I'm going to use -1, and then it'll be 1, 1, -4, -4. Bring the 1 down, so 1 times -1 is -1. Add those together, I get 0. This becomes 0. -4. -4 times -1 is a +4, which gets 0, which is what I want. So there's kind of a checkpoint in my problem that, yep, I got 0. That's what I want. So now my 2 factors are going to be x plus 1 times x squared plus 0x minus 4. So that's synthetic division. That gives me the coefficients. And remember, I'm trying to make this equal to 0. So I know then -1 is a 0, which I've already confirmed. X squared minus 4, this is x squared equals 4. So x is a plus minus square root of 4. So therefore, x is plus minus 2. All right, so that one, obviously, we went through that one a lot faster. Second time through, and the more times you do it, the quicker it'll be. All right, but you just follow this process. Constants divided by leading, those are all your possible ones. Use your remainder theorem to figure out which one equals 0. Once you got one, use synthetic division to create the second factor. Solve that for the zeros, and you're done. Okay? All right, so I was going to do another one, but we're good. So IXL, L10 to a 70, and then IXL, it's like identifying coefficients and stuff like that. It's not actually doing one of these whole problems in there. So IXL, Algebra 2, L10 to a 70, and then these are the only two problems that I want you to do. Okay, they're in Schoology as well as a PDF, but I put them up here so you can do them right here in class too. So exactly what we did on those last two example problems. State the possible rational zeros and find all zeros, and be ready to turn these two in tomorrow. Okay, it's only 2 questions. It's going to take a little bit of time, but it's not going to be terrible since